Good morning, everyone, and welcome to our presentation. First of all, let me thank you all for coming here today. Let us introduce ourselves. We're both from the States, and I'm Take Kong from Alabama and Jin Cozio from Louisiana. What we would like to present to you all today is DeepNote GNN, predicting hospital readmission using clinical notes and patient networks. The motivation of this project is to reproduce DeepNote GNN and present the pros and cons that we have faced as an easy and hard of implementing the model. Finally, we'll be assessing DeepNote GNN on the reproducibility based on experiments. We thought it would be useful to divide our talk into 7 main sections. First of all, we would like to give you an overview of DeepNote GNN. Secondly, we'll focus on approaches and methodology we have employed for DeepNote GNN implementation. Next, we will introduce the evaluation metrics we have utilized for comparing the model performance, and then we will consider the hyperparameters for better model tuning besides DeepNote GNN. Finally, we will be dealing with the result and conclusion beyond improvement and future work.
Let's first give some background of this project. Clinical Notes contains information about patients that goes beyond structured data. And with the increasing availability of electronic health record and advances in deep learning techniques, building deep predictive models that use EHR data are studied recently. Still, learning clinical outcomes from all possible information sources is one of the main challenges when building predictive models. In 2021, Gourmet and Luo focus on two sources of information that have been underused by researchers. First is unstructured data like the clinical note, and the other is a patient network. And they propose a hybrid deep learning model, DeepNote GNN, that integrates these two parts of information to improve 30-day hospital readmission prediction. And in this project, we implemented the model proposed in the Gourmet and Luo's paper and reproduced the results. Now let's introduce the DeepNote GNN model. This is the architecture of the DeepNote GNN. DeepNote GNN contains two parts, DeepNote part and the patient network part. DeepNote is built on top of a BERT model that generates the representation of each admission. And using the representations, a patient network is built and a graph neural network model is applied to do the classification task. And let's look into each of the parts together. The DeepNote part of the model is mainly to generate a representation of each admission data. For this part, we first get the admission data and the clinical notes related to each of the admission from the dataset. And each admission is denoted as AI, and the related clinical notes are denoted as NI, which will contain multiple clinical note data. Then we feed clinical notes related to each admission to the state-of-art natural language processing model BERT to obtain the representation of the clinical notes. Since BERT takes 512 sequence input at a time, we split capital NI into text chunks with smaller lengths. Then we use Clinic BERT, a BERT model pre-trained on the clinical dataset, to get the token sequences. In each of the token sequence TJ, the first token is a special classification token CLS, and we denote this as FJ. And this is the final hidden state in BERT, and it is used as the aggregate sequence representation for classification tasks. After pre-process the test in Clinic BERT and get a set of CLS, on top of this, DeepNote is implemented as an average feature aggregator to compute the admission features directly from the embedding, FI, following this equation. Utilizing this average aggregator allows admission feature become an overall picture for all text chunks related to it. And then we will use this as the deep representation for the admission AI. Once we got the deep representation of the admission, a patient network is built based on the representation and a graph neural network model is applied to do the classification task. The patient network is modeled by a graph G. It contains a knot set V. Each knot is a patient's admission. The deep representation of the admission will be the knot properties. And E is the edge set of the graph. Two admissions are connected by an edge if the cosine similarity of their knot properties is greater than a threshold theta. After obtaining the graph representation, we apply the two-layer graph convolutional neural network GCN for the knot classification test to predict readmission or not for each node. The two-layer GCN model computes the class score Z using the following equations, where A is the normalized adjacency matrix of the graph G, and X is the matrix of all node properties, and W0 and W1 are weight matrices of GCN. If Z is close to 1, we say there is a readmission for the node, and if Z is close to 0, we predict there is no readmission. Using the training data, we can obtain the deep representation and the patient network. Then with the known label in the training set, we can learn the weight matrices W0 and W1 and further use the trained model to predict the class score for new admission. The dataset used in this project is the MI-MIC3 clinical dataset version 1.4. As mentioned before, we mainly use the following two files from the dataset: admissions data and clinical notes data. For comparison, the same data preprocessing is used as in the clinic BERT paper.
In this part of our presentation, we would like to talk about the evaluation metrics we have employed for comparing the model performance. We use accuracy, precision, RP 80%, and RC, which were utilized by DeepNote GNN paper. Additionally, we utilize validation loss for measuring the loss rate besides BMIC3 clinical dataset. Accuracy, precision, RP 80%, and RC were calculated by sklearn. Finally, we generated the graph of evaluation metrics that represents the final result of DeepNote GNN after adjusting hyperparameters. Next, we will put you all in the picture about the hyperparameters. There are hyperparameters for the reproduced models such as learning rate, epoch, patient value, window size, batch size, optimizer, and so on. The above table represents the major hyperparameters we have set our eyes on the most of the time. We random search by adjusting the best fit hyperparameters for model optimization. Finally, we will discuss in more depth the implications of reproducing DeepNote GNN. Comparing the evaluation output based on the paper, we perform slightly better on RC of 0.0012, the precision of 0.0035, and RFP 80% of 0.3074. We assess that DeepNote GNN is positively reproducible. Although we have spent longer implementing the model, DeepNote GNN is executable and show high precision and RC scores. Otherwise, DeepNote GNN is a hybrid model which is combined with the clinical BERT and GNN. This makes the model 2 times more complicated to deploy. Furthermore, adjusting hyperparameter is another time-consuming job for reproducing. We therefore strongly recommend implementing a genetic algorithm for the optimal solution. We will make a detailed explanation of genetic algorithm. Genetic algorithm is a stochastic gradient descent algorithm for model optimization and supplements shortcomings of random and research. GA provides multiple optimal solutions and allows global optimization. This algorithm is utilized in the image classification industry like YellowV5 to suggest an optimal hyperparameter solution. Even though we are highly satisfied with the outcome, we can challenge applying the genetic algorithm to DeepNote GNN for model tuning and better evaluation results. We have now come to the end of our presentation. To sum up, DeepNote GNN is obviously reproducible beside the BMIC3 clinical dataset, and we are satisfied with the final result of reproducing the model. To perform better evaluation results, we would suggest utilizing a genetic algorithm for model tuning.